All right, we should be live for World Quant office hours. Let me just make sure that I am streaming. Yes, I believe I am streaming. Let me go ahead and re-up. There it is. I see myself now. All right, so welcome to Unit 2 Office Hours, Week 2, Office Hours 3. Let's see who is joining us today so far. All right, see Emmanuel. Welcome back, Emmanuel. Nice to also see you today. I see Esau. Welcome back, Esau. Yes, thank you for the confirmation that I am streaming and going through properly. And our goal here is to pick up on our mini project, pick up on our progress on our mini project. We worked on Q1 yesterday. Those are lots of great stuff to talk about with Q1. Lots of great stuff to talk about. And as always, just because we got the right answer doesn't mean we are done and satisfied, right? We're trying to be introspective, to be critical of the code, be critical of the solutions we offer, and see if there are ways to improve it. And that's what happened last time, where we said, you know, we're not too happy with what we have. Let's go and improve it. And I think we have an improved solution, for the mini project. So let me go ahead and get back to where we were, and I'm trying to recall, was there anything else I wanted to speak of about Q1? Let's see, anything else that I wanted to mention about Q1? I don't think so. I don't think so. Sorry about that. So I think we're ready to move on to Q2. So I see more people have joined us so far. Raul is here. Welcome, Raul. Jay, nice to see you again. Jay, I see Akpalai Fico. Welcome, Akpalai Fico. Mickey Rat is here. Welcome, Mickey Rat. Fatima, Sahid. Welcome, Sahid. Any leftover questions about Q1 before we proceed to Q2? Just want to make sure that we got those things covered before we proceed on to Q2. All right, Aaron is here. Welcome, Aaron. Okay. Well, do let me know if there's any holdovers from Q1. Sorry, let's go to Q2. And nursing homes vary greatly in their business characteristics. Some are owned by government or nonprofits, others by a run for profit. So some homes, a few dozen residents, while others have hundreds. So there's lots of things that can differentiate the different nursing homes, right? Whether they're government owned or if they're private for profit, how many residents are in a home. So maybe we can use these characteristics of a nursing home to predict how much fines they will incur. All right. So let's look at our data, which we call X. I think we call it data. And quite a few number of columns, so I can say dot columns. And here's all the columns I have. But let's go ahead and work with just these columns here for right now. There's all these sets of columns. Let's create a model that's going to use these columns. So what we've also provided is we provided a custom transform called column select transformer. Modern versions of scikit-learn have a very similar built-in tool called column transformer. But because of the idiosyncrasies of that transformer and the idiosyncrasies of our grader, we're going to use our own column select transformer instead. And what it does, the way it works, is we give it the columns, and it's going to select the columns from the data frame. So in other words, if I were to sketch out how this transformer is going to work, we have our data here. The first thing we should do, should probably convert it to a data frame to make it easier to work with. And then we have a transformer that will select certain columns so that we can feed it downstream. So we're going to have initially 2 steps, at the very least 2 steps. Conversion to data frame, select columns, and then move on. And we already provided to you this transformer that's going to select those columns. However, let's be critical about this code here. Right, let's criticize even some of the code that we provide for you, right? What would be your criticisms of the code we provide for you here? There's something about this that I just don't like. I just don't like. What is that? What are your thoughts? It's time to be critical. I see some other people here. I see Adeyeye, Joakim, and Vincent. Welcome. The if else. There's something. Well, I guess we could have if else, right? But no handling of NAs. So it's not handling NAs. Well, let's first go back to the point someone brought up about if else. I guess we could have said if not else. But that's okay, right? That's sort of just a flavor. So I'm not too critical about that. Handling NAs. I don't want to handle. This doesn't handle any missing values. That's correct. But the sole job of this transformer is just to select. One of the things we want is we want to compartmentalize things. We want things to do one thing right. We don't want things to do multiple things. So we could do some handling of NANs, but that's perhaps better served by a different transformer. But now that I mentioned this idea of doing more than one thing, does that clue you into some of my criticisms of this class that we have here for you? There's something about this class that I just don't like. This class should have one job, and that is to select the columns. So what do you think is bothering me about this code? It's really this part here. Notice what this class is doing besides selecting columns. It's transforming things. Yeah, exactly, Esau. And I don't like my transformers to do more than one thing. So for example, I have a transformer that's about scaling my data. It should just scale my data. Shouldn't do anything else. Shouldn't be transforming things to data frames, right? That's really a job for a different step. Exactly, Fatima. We already defined a transformer to do that just does that. Let's compartmentalize it. Let's not have a transformer that does more and more things. Because you might say, oh, it's just this here. It's just this here. But notice how annoying it is. Because I have a check here. And then earlier, the code we gave you for the group mean also had a conversion. And it's like, why do we keep on doing that? We just have a separate step to do that for us. Do it once, not have to worry about anywhere else. Let's not have a transformer do more and more work. It's just got one job. Let's have it stick to it. Because if we let it do, the conversion to a data frame, and then, let it do the conversion of missing values, we're going to end up having a transformer that's just doing way too much. So yes, exactly, Esau, I don't like this here. It should just simply select the columns, not the conversion right there. That's what we should have instead. So, the code we provide isn't perfect, right? There's problems with it, and at least I have problems with it at times. That's why you got to be critical. So now we have a very simple pipeline that just selects the columns, but of course we should have a previous step, right? To data frame. And let's have the to data frame object right there. So now we have a two-step process. Do the conversion, select the columns. So now we can go ahead and see what we're working with there. We're going to attack data. And we're going to look for if we have missing values. And looks like we have an isNaN. Let's see what's going on here. A type error because ufunc isNA is not supported for the input types. So let's see what happens when I call data. And what I probably can do is convert this into a NumPy array, and then I can go ahead and say something like any. And let's see. I guess we're trying to figure out how many null values there are. So this comes out the data frame. I can just say something like is null, or maybe just info. Call the info method. And what we're trying to observe here, we're trying to point out here, is the fact that there are certain columns with missing values. Looks like what comes out of our data frame, what comes out of our pipeline, this two-step process, a conversion to a data frame and select the columns, is a data set with missing values. That's what we observe here. Notice we have non-null values. We're missing some of them. We're missing some values in our table, in our data. And this is a problem here because our predictor, our downstream predictor, it wants numerical data. It doesn't want missing values. Here's our predictor. Of course, the question becomes, what should go right here? Anything else that needs to happen right here? And we observe that we have missing values. We need to fix that. So scikit-learn is going to provide us a tool to fix missing values. And that's through the simple imputer. So let's add one more step here, which is our imputation step. So right before we give it to our predictor, we got to ensure we don't have any missing values. So from scikit-learn, import simple imputer. And since we've never played around with this class before, let's look at the documentation. Right, let's understand what it's doing. Imputation transformer for completing missing value. So basically, impute, just a fancy way of saying, oh, you got a missing value. Let's impute it. Let's put a value, a valid value in there. If we look at the documentation, missing value. So how does it recognize a missing value? NaN by default. And then we have strategy. Okay, so it looks like we can dictate or we can control the strategy to use it to replace a missing value. Just like yesterday I mentioned, if we didn't have someone's age and you wrote down their name, guessing whether a newborn may not be the best guess. Guessing something like a statistical value of our population, like the mean of the median, is probably a better guess. So it looks like I can control the strategy it's going to invoke to replace those missing values. So let's go ahead and try that out. My imputer equals simple imputer, and strategy I'm going to set to mean. I'm going to set to mean. We can argue whether what's the best one. We'll just set something there. Let's play around with it. Let's get it to work. And let's go ahead and get the data that comes out of our pipeline. So what we called it before, we called it simple features. Simple features. Let's call it transform on data. We'll call this x of t. X of t that comes out, and we'll look at the head of x of t. And now what we'll do is we'll say imputer fit and transform on x of t. What comes out as a numpy array, we'll call that x of tt. And let's see if there's any missing values. And I can perhaps call the isNaN function in NumPy, which returns to us a Boolean array of whether we have a missing value or not. And I can call any to see if any of those are missing. And we have false. So now we have a transformer. Makes sense as a transformer because it takes it and is going to transform it. That will replace the missing values with the average for that column. So in other words, if we're missing values for, let's say, exponential total, notice how it's NaN, we're going to fill it in with the average for that column. And if we're missing any values for adjusted total, we're going to fill it in with the average for that column. And that's our simple imputer. Questions people have right now? A question here about hello everyone, what is start my server, right? Start your server. If you go to control panel, we'll start your server, right? We'll start your server so you can access your account. So make sure when you log in, you put in your username and password. You'll see start server. You hit start server. Then your server starts up so you can access the content, work with the grader, or do the mini project. So that's what that does, Daniel. Okay. Well, if there are no questions, let's go ahead and try it out. Let's go ahead and include our simple imputer. Our imputer. There's our imputer. And then we need a regressor, right? We need a regressor for our model. And I'm not really concerned about performance right now. I just want to get something that works, that can get a grade from the grader, and then I can go and improve. Right? Now, let's not go for the more complicated models that take time and effort. Let's start with something simple. Let's try it out, and let's see if we can do a better job, right? It's an iterative process. So I'm going to use, for my regressor, I'm going to use a very simple linear regression. So I apparently don't have it imported. At least tab autocomplete isn't helping me out there. So linear model, import linear regression. So I create my model. I got to fit it. There it is. I just want to predict whether the find counts are greater than 0. And now I'm ready to pass it to the grader. I get an attribute error. So let's examine what that mistake is. Linear regression has no attribute predict probability. Because we're doing classification. We're doing classification here. So I should import logistic regression instead. So sorry about that. A little mistake there. A linear logistic regression. And my score, hey, not too bad. Not too bad. First effort, right? 0.996. Right? Tried out my first model as possible, got 0.996. There's nothing wrong with trying a simple model first, right? Just as a benchmark. So now I can make sure that any model that I develop from here on, I should compare it and see if it does better. Questions you have before I go back and see how I can improve this model? How did you handle the array coming out of the imputer? How did you handle the array coming out from the imputer? That's where I'm doing the pipelines. Because what comes out of the imputer then gets fed into the logistic regressor. I'm not sure if that's your question, but do let me know if that's what you're asking, or do clarify. So data frame array, okay. So, okay, how did you handle the array coming out of the imputer? So data frame, array, data frame. Okay, so we have a transformer that's going to return a data frame. Column transformer is going to select the columns and pass a data frame. The imputer transformer, like most transformers in scikit-learn, can work with pandas data frames. Just what happens is that what they return is a NumPy array. So one of the things we observe here is that in scikit-learn, the predominant behavior is they can accept things like lists and pandas data frames. It's just that the output will be a NumPy array. Because in a pandas data frame, we have the values attribute, which returns a NumPy, the underlying NumPy array. So while the simple imputer will get a data frame, it will just simply do dot values. So that's sort of handled in the mechanisms of scikit-learn. If I give it a list of lists, it will convert that into a data frame. I mean, a NumPy array. Now you can argue, well, now you have these steps that are doing work of other things. Yeah, that's what happens. But hopefully they've done it in a more efficient, a more elegant way in the code base, right? You can think of they have a maybe a decorator that will do that check for them. So why do we need to create the object function instead of working with fit and transform directly using scikit-learn? Why do we need to create the object function instead of working with fit and transform directly using scikit-learn? So is your question why I just give it the object here in the pipeline and why I'm not calling fit and transform individually? Is that your question, Fatima? Of why I just put the transformer, the estimator objects in the pipeline and not have to worry about calling in fit and transform directly on those objects? If that's the case, the reason being is that the pipeline takes care of that for me. The pipeline would take care of that, all that work for me. Imagine I don't want to call fit and transform all the steps myself. I don't want to keep track of the intermediate transformations. The pipeline will take care of all that nicely for me. Is K and N only for discrete values? No. K and N can be used for regression and classification. Other questions you have? Yes, we create it. We create the object, right? We can create the object. So a little different. Let me show you just a little subtlety that might be a little confusing. Is notice these are objects that I created before, and here I'm creating it right there and then. So I could have done this. I could have said classifier, and then put it here. So you could have done it this way. Where we have create the object right there, or create it outside and put it in there. Either way, notice we're not fitting it ourselves. We did for the imputer and the other stuff because we're sort of experimenting. We're showing, kind of letting you know what's kind of going on, making sure we understand it. But now we get it, and let's let the pipeline take care of it for us. No need to apply fit and transform each time in the process. Exactly, right? We call fit once, and then we'll call fit and transform on all the transformers, and then fit on the predictor. It will keep track of those intermediate steps, those intermediate transformers. And yes, Ramsey, we could have used K and N here. In fact, let's try that out. From sklearn neighbors, let's import K and N classifier. And then what I'll do here to make my code a little bit easier to maintain is I will create the classifier out here, and then place it right there. So let's try this version with K and N to see how well it does. And not so great. Not so great. At least our first effort, 0.5, not so great. True Friend is asking, do we have to use the sorted steps in the pipeline? The order of the steps matter. The order of the steps in the pipeline matter. So I cannot have things kind of mixed up. I need to dictate the order. I need to make sure I place them in the correct order. That's sort of a burden on me, but hopefully I know, right? I should, right? Scikit-learn has no way to know that you want to do that one before that one. No way to know that. Way too complicated to code. That's a little burden on us that we have to give it the order of the steps, which are our simple features pipelines. So you can have pipelines and pipelines, right? The simple features was simply 2 data frame, select, and then the imputer and the classifier. So Ramsey's saying, well, we haven't done any kind of cross-validation, right? We have not done any kind of cross-validation. Yeah, we have not done any kind of cross-validation, so we should probably do some cross-validation, right? To see maybe we can do a better job. So let's try that out. Let's see, hey, we can probably do a better job. So let's try that out. I'm going to copy this and just paste in a different cell. And let's say from sklearn model selection, let's import grid search CV. And then what I'll do is I will create my grids. create my grid search object right here. Pass it the classifier. And I'll just comment the first line out, this one out here. And I'll give it a param grid. Let me construct a param grid, and that param grid is I want to tune the neighbors, and I want to search through maybe, let's say, 2 to 20. 2 to 20. We can change it afterwards. So let's just try it out. 2 to 20. Param grid. Let's use 5 folds, and let's say verbose equals 1, so we can get a print out of what's going on. Let's put the grid search object right there, and let's fit. And I get a value error, so I probably have some sort of mistake. Let me go all the way to the bottom. Invalid parameter neighbors. So it's telling me that it's called something else. What did I do wrong here? I know what I did wrong, because I'm asking you what I did wrong. But I made this mistake not on purpose. What did I do wrong here? It's called n neighbors. Just make that fix. N neighbors. Yeah, n neighbors. Thank you, Ramsey. And it's spelled the American way, so we just gotta, spell it the American way. I'm not saying the right or wrong way, right? There's just the British way, there's the American way. Not one way is better. Not one is better than the other. But since I guess most of the package maintainers are American, it's spelled the American way. And we did that. We've tuned it, and let's submit it to the grader, and we did a slightly better job. But let's examine my grid search object. Let's look at best params. The best parameter was 18. The best number of neighbors is 18. So that is probably telling me, what does this tell me? Let me ask you this. Now I figured out the best number of neighbors is 18. What should I do next? Should I stop my search, or should I modify my search? So let me know. I see Daniel saying, I think 520. I'm not sure what you mean by that, Daniel. Are you trying to access our hub and you're getting a 520 error? Or do let me know what you mean by that. Yeah, Ramsey, correct. You're correct. We should probably increase our neighbors because our param grid that we used went from 2 to 19. So the best number was right at the edge of our grid, or near the edge of our grid. Maybe we should expand, right? Maybe we should expand. Looks like things were getting better and we stopped. So let's tweak, right? It's an iterative scheme. Let's tweak. And let's say go from, let's say 15, and let's, say 50. Let's try that. Let's try that now. Let's see what we get. It's taking a little while now because there's more things to fit. But nonetheless, this should hopefully run in some time. So that's why it's the nice thing about setting verbose equals 1 is that it's printing out what's going on. So I can know, oh yeah, it is running, and not saying, is it running? Well, I know pretty sure that's running. Okay, that ran, and that took about, let's see how long that took. About 30 seconds. That felt longer, but oh well. Let's see what the best neighbors are. It's 46. Oh, so it looks like it indeed made sense for us to expand the range. Let's submit to the grader. Oh, we got better results. However, once again, my best number of neighbors, my best value, the hyperparameters, near the edge of my range, near the edge of my grid. So maybe we should expand further. Let's try that out, right? So let's start with 40 and let's go up to 100. And let's try this out. And let's see what answer we get. And while we wait for this, let me know if there's anything I should examine. But thank you, Ramsey, for suggesting a different classifier, so we can play around with how we go about tuning its hyperparameters. Can you plot it so we can see it? We can also plot the results. Right? We can plot the results, which is fine because we are just tuning one hyperparameter, so it's easy to visualize it. So we will do that, Ramsey. We'll do that just in a bit. Increased neighbors may increase. Yes, exactly. So True Friend is bringing up a point here that if we increase our neighbors too much, we might have actually underfitting. Actually, it's the reverse. Too few neighbors, we overfit. Too many neighbors, we underfit. And it sounds a little bit counterintuitive, but let's consider the edge case. If our number of neighbors is the entire data set, so we got 1,000 points and we have 1,000 neighbors, we have a model. How many different, let me ask you this. If we have a model that has 1,000 data, 1,000 points, and we have 1,000 neighbors, how many different values does the model predict? How many different values will the model predict if it uses all points as the neighbors? As we use these models, it's great to get an understanding of how the hyperparameters affect bias and variance, overfitting and underfitting. We'll do the plot, and I'm still waiting for responses. So let's do grid search. CV results is a dictionary with the results, and I forget what the key's called, so let me look at keys. Mean mean test score. Mean test score. And that's my Y, and my X is simply my param grid neighbors and neighbors. Let me make sure I import matplotlib, import matplotlib dot pyplot. That's PLT. And there is, let me just put some axes on there. Y label is average score across K folds. And notice what we have here, that even now the best parameter was 94, and it looks like we're still increasing, so maybe we should further increase our neighbors, right? There's some, of course, some undulations and some variations, but the general trend is that as we increase neighbors, we get better and better results. And our best score, our best parameter was near the periphery, so we should probably once again repeat the process. So thank you, Ramsey, for reminding me we should plot this. And I'm going to be rather aggressive. I'm saying 90 to 200, step of 2. Now let's try this out. Oh, I forgot to submit it to the grader. Oh, wow. All right, so let's see. I got some, after CV, the pipeline will predict using the best model. Correct, exactly, Mickey Rat. After the cross-validation, when I use a grid search, it will automatically use the best model. I could pull out the best model using best estimator attribute, or I can just be satisfied that the grid search object is automatically going to use the best model it found. And in fact, it retrains the model one more time using the entire training data, using the best hyperparameter. So what do people think? What if I have a nearest neighbors model that relies on neighbors to come up with a calculation of a prediction? I use all the data in my data set. How many different values can it predict if it's using all the data in my data set? That finished. Oh, look at this now. Look at this now. It was increasing and then a sudden drop. So this is telling me that maybe we did indeed found the optimal value now, because the best answer is somewhere in the middle of my grid. So I probably don't need to push this further. And I get a 0.9. So good for honors, right? Good for honors, but it looks like maybe using nearest neighbors algorithm is probably not going to outperform our logistic regressor. Of course, it's always data dependent, right? We don't know this ahead of time. That's why we do these experiments. So yeah, looks like we probably got the most out of our nearest neighbors. And going back to the question I asked, if my nearest neighbors algorithm uses all the data, it's only come up with one prediction, right? It's the average of all those points, or the majority class. Well, that's a simple model. If my model only gives me one result, it doesn't really make use of the data, the features. That's a very simple model. It's an underfitted model. So actually, as you increase the neighbors, you lead to underfitting, high bias. And as you decrease the number of neighbors, if we just rely on a single neighbor, we are at the whims of our data set. What just so happened to be our nearest neighbor? Our model's performance will be widely different depending on what just happens to be our training data. It's too dependent on the training data. So if we were to have too few neighbors, we overfit. Too many neighbors, we underfit. Then the question becomes, then we do these tuning to figure out what is the optimal value of neighbors. In this case here, about 150. Questions you will have? How do you pick between the mean and median? Okay. So going back to strategy, well, we could, right? We could Okay, Ramsey brings up a point. Well, what about our imputer step? How do we go about picking mean, median, and mode? Well, we have to do an experiment, right? We don't know off the hand, although our prior experience is probably going to point to us using the median. The prior experience probably telling us we should use the median because the median is why. Let me throw you this out here. Why is it preferable that we use the median instead of the mean at times? Anyone want to guess why that's the case? Any guesses? Why is it that if I don't know anything else, I should probably rely on the median instead of the mean? The median is generally less susceptible to outliers. Medians are less susceptible to outliers. We're going to have an outlier that's really going to affect the mean, but for the median, it's just the middle point. So outliers are going to affect it less. So it depends, right? The mode, median is the middle value. Wouldn't mode be better because it's the most frequent? Well, maybe, who knows, right? Who knows? Maybe so. If our x is normally distributed, then the mean, median, and mode are all the same. But maybe the mode might be something better, right? We can make some arguments here. We can say, well, I think the median would be better because it's less susceptible to outliers. The mode is less susceptible to outliers because we are taking the most frequent. But it's going to be a discrete value, right? If we take the mode, if we're dealing with continuous values, may not be the best thing here. Because maybe the mode of 0, maybe 0 appears so very often. But the average is maybe, let's say our numbers range from 0 to 100. And the average might be, let's say 55, let's say 45. But there are a lot of zero values. So the most frequent number might be 0. But that doesn't really represent much about our data, our population. So mode doesn't make sense when we have continuous values. If we have discrete values, I can argue that the mode would be the natural choice to use. Either way, we were using our own experience to come up with a good guess. Our own experience says that mean is more susceptible to outliers, so maybe median, and mode only makes sense when we have discrete values because 0 might be the most frequent, or 1 might be the most frequent, and there might be other continuous values like 45.12345 only appears once, 45.67 also only appears once. So we can just guess and say median. Or we can run an experiment. Right? We can have our guess and we can back it up. But until we run the experiment, we don't know. And luckily for us, we have tools in scikit-learn to allow us to run these experiments. So now what I want to do is I have wrapped everything into a pipeline here. Why didn't we plot the data before guessing? We could have plotted it, right? We could have plotted it. But once again, we won't know until we run the experiment. Right? So I could go my data. And let's see. Data. Let's see. What was one of those columns that are missing values? Let's see. something like adjusted total has missing values. So if I say value counts, the most common value is this number here. I can visualize that. Do a histogram. So maybe 4 is probably the most common. Actually, 3 is. And I can take the average. That's the average. And that's the median. So it looks like 3, 3.8, and 3.7. But now let's actually run the experiment for us to know which one is better. So what we could do is we wrapped everything to a pipeline, and now we're going to apply grid search on the pipeline instead. Instead of having grid search as our final step, we're going to pass the pipeline to our grid search. So what I'll do there is I will create a new cell. Let me just go ahead and copy this there. Copy that right there. Let's actually go back to, let's stick to KNN, right? Let's stick to KNN. And what I'll do is I'll still have my classifier here. It's just, I have my param grid and my grid search, but I give it my pipeline. So it's a little different here, where I'm, instead of grid search being my last step of my pipeline, I'm going to apply grid search on my pipeline. And that will allow me not to only tune the estimator, the hyperparameters of my predictor, that will let me tune the hyperparameters of all the other steps. For example, the strategy I used for my imputation. So what I'll do there is I'll break this out into multiple lines. And since that step is called regressor, I have to call it regressor dunder number of neighbors and neighbors. And then I can say imputer dunder strategy, because remember that was what is called strategy, and say mean, median, and most frequent. Why didn't it say mode? I don't know. I think it would have been logical to say mode. It's called most frequent. And now let's try this instead. And the point I want to stress here is that we can always try to come up with guesses. We can always guess and come up with some good guesses on what should be best, but we won't know until we actually carry out the experiment. I get a value error, so let me see my mistake. Go all the way down there. And neighbors for grid search. So let me just go back there. It's called, I should really call this something else. And this should have been my classifier. And this is not a regressor, it's a classifier. Yes, the name is arbitrary, but let's not drive our colleagues crazy. And now it's doing it. Now it's fitting. Let's see a couple things in the chat here. A quick one. Each time before making a guess with real-world data, would it be advisable to evaluate the various strategies before confirming which one to use now? I think it's best to outline your options. Outline your options. What ends up happening, Esau, is that those options might be a lot. There might be a lot of options. And we cannot try everything, so you really should narrow down your options. So things like imputation, the best thing to do is probably median if we are dealing with continuous values. If we have categorical data, which we'll play around in Q3, the best thing would be most frequent. Same thing with scaling. In scaling, typically standard scaler is the best. So we could perform an experiment trying out different scalars, but let's just narrow down our options. So what I would recommend, Esau, is kind of what you point out. Consider all the things, all your options, and knock a couple of those like it's kind of inconsequential. We're splitting hairs. We're fighting over small things. Can we change the CV number to increase the accuracy or increase we could increase the number of folds, which will make our experiment more precise, make our experiment have more statistical meaning. That's what the number of folds would do. The number of folds won't necessarily improve the model. The number of folds doesn't improve our model. The folds improves our experiment to find the best model. Think of it as a number of trials. This is slow because there's a lot of things to fit. So I probably should have maybe, done a finer, a more coarse mesh. But oh well, I made my bed. Now I got to lie in it. And we can take answers. I'm going to take questions people have. All right, great to hear that you got that ESAL. Good question you brought up, so thank you for bringing up that question. It's still chugging along. This will probably take a while, so we can probably spend all the rest of our office hours trying to improve this model. But I will let you tweak it further. We could include additional features like polynomial features to try to improve our model. We didn't tune our classifier. We didn't tune our logistic regression classifier. So that's something we could have done. We focused on n neighbors. I think the drawback of the embedding pipeline, I think that is a drawback of embedding pipeline in grid search. Yeah, that is a drawback because technically it's going to fit and transform all the steps on the entire chain. So it's going to be slower. It's going to be slower because it has to fit and transform all the entire pipeline as opposed to if it was a final step, the predictor. But this does enable us, this does allow us to run experiments on the different transformers, on the experiment on which hyperparameters of our transformer we should do. So it's sort of a trade-off once again. But that's good that you realize that drawback, Suleiman. If we were just focusing on our predictor, which we did earlier, then what we did before, where our grid search was the last step, made more sense. So obviously this won't run before the end of office hours. But anything else we want to bring up before we conclude today, and then tomorrow we'll pick up on Q3. Okay, we'll pick this up tomorrow. With that, everyone, take care. Have a good rest of the day, and we'll see you back here tomorrow. I will let you know what the final results are, because it will take a while.